Proof of generalized beta integral, or also called Dirichlet integral, by induction. So this integral given over here is actually the generalization of normal beta function, right? So we usually read about this integral from 0 to 1 of, let's say, t to the power a1 minus 1 and then 1 minus t to the power a2 minus 1 dt. If this is the case, we know that this is just the beta function of a1 and a2, and that was gamma of a1, gamma of a2 by gamma of a1 plus a2, right? So we are just trying to generalize this integral, and in n dimension, this actually becomes like integral over this n-dimensional simplex. I will tell you what that is. Our domain is n-dimensional simplex, and then now what we have is all these variables, right? There are n xn's, right? And then there's also this 1 minus x1 minus x2 up to minus xn, and this is an plus 1 minus 1. And so what this becomes is, just like earlier, first of all, we will have product of all these ai's, right? And also we have an plus 1 over here, all of this, divided by the sum of all of these, a1, a2, up to an plus 1, right? So yeah, this is the generalization of the beta function in n dimension. And yeah, so we're gonna prove this fact. But before we do that, let's talk about how this n-dimensional simplex looks like. So here also there are some restrictions, like n should be greater than equals to 1, ai should be positive, and then this gamma is the gamma function, which is generalization of the factorial, right? So we know this. First, also let's first understand how n-dimensional simplex looks like, and then we'll go to the integral, right? And then it will be more intuitive. So on this domain, on this n-dimensional domain, is defined as like sum of all these coordinates in like Rn, right? Because there are n coordinates, and each of them is positive, and the domain is given by the fact that the sum of all the components of the coordinate is less than equals to 1, right? So this is how we define our n-dimensional simplex. So let's say in one dimension, let's see how this thing we can see in one dimension. In one dimension, this is just a set of x1 such that x1 is positive and x1 is less than equals to 1, right? So okay, now what happens is, let's say I have a one-dimensional coordinate, that means a real number line, so and 0. So what happens is, all the set of points x1 such that x1 is greater than equals to 0 but less than equals to 1. So that includes all the points between 0 to 1, right? Yeah, because all of them satisfy the fact that they're greater than 0 and less than equals to 1. So this red region is basically our T1 domain. Okay, so this is basically our domain T1. So in one dimension, the integral. Okay, so in one dimension, the integral will just be integral from 0 to 1, because that's our domain, and then our n is 1, so T1 to the power a1 minus 1, and just that, right? And then 1 minus t 1, I can write t1, it doesn't really matter, but I can, yeah, t1 to the power a2 minus 1 dt. And this was gamma a1, gamma a2 by gamma a1 plus a2, right? So yeah, you see this in one dimension. Now let's see in two dimension. We are just trying to get the feeling before we get to the proof, okay? Because this will help you later on. So now, for two dimension, our t2 will be defined as the set of coordinates x1, x2, such that all these xi's are greater than equals to 0 and x1 plus x2 is less than equals to 1, right? Okay, so now let's take a 2D coordinate system. Okay, and this is the origin, right? So we want the coordinates to be positive, but also it's restricted by the fact that their sum should be less than equals to 1, right? So first of all, what you can do is, let's say this is x1 coordinate, x2 coordinate. We can first of all draw x1 plus x2 equals to 1, which will be this line, right? And satisfy the inequality, like all the because origin satisfy this inequality, right? So all the points just are towards the origin from the line, so that turns out to be all these points will satisfy that inequality, right? So you can just take a point. Let's say if you take 0.1 comma 0.1, so this point, that will be 0.2, which is less than equals to 1, right? So let's say if you take this point, half, half comma half, right? Half, half, that will also be 1, and that's included there, right? So basically when you take the equality, that gives us the margin, the border line, and then since origin satisfies, so we know that all the points towards the origin from this line will satisfy the inequality, right? So yeah, so we get this domain, and this is basically our this domain T2. So this serred thing is basically our domain T2, right? So I can say this as this is our two-dimensional simplex. Two-dimensional simplex, right? This was our one-dimensional simplex. Okay. And over here, now, like if we want to write the integral, so we knew that okay, over this two-dimensional simplex, so which we can write as, in x1 we can go from 0 to 1. In x2 we will basically go from 0 to 1 minus x1, right? Because this line is basically x2 is equals to 1 minus x1. Yeah. So yeah, okay, so this is our domain T2. So in this domain we now know that x1 to the power a1 minus 1, x2 to the power a2 minus 1, 1 minus x1 minus x2 to the power a3 minus 1. So this will just be gamma of a1, gamma of a2, gamma of a3 by gamma of a1 plus a2 plus a3. So yeah, so we have also seen how the beta function is generalized to like two dimension, right? I mean, you can also see this as three numbers, but yeah, basically this is two-dimensional beta function. Yeah. So now let's also see for three dimension, and then we'll go to proof. Okay, like just one more, because from this demonstration, I'm also trying to establish something important, which will be helpful later in the proof. So that's why it's necessary to do this right now. And I hope you are not bored. So T3 will be the set of coordinates x1, x2, x3, such that this xi is greater than or equals to 0, and x1 plus x2 plus x3 is less than or equals to 1, right? Okay, so now we need to have three dimensions, so it will basically be like this and this. This is x1 coordinate, this is x2 coordinate, I mean axis, and then this is x3 axis, right? Okay, so we know that all of these x1, x2, x3 should be positive, and also that x1 plus x2 plus x3 should be less than or equals to 1, right? So first of all, for the boundary of our, okay, for the boundary, we already know that this should be positive, right? So what happens is, like this x1, x3, like this, what do you say? This region, actually, the region, I mean, what I mean is the plane. Yeah, actually, the plane of x1, x3 will be one of the boundary. The plane of x2, x3 will, let me say it slowly. Okay, the plane of the x1, x2 will, this will be also one of our boundary, right? And the plane of x2, x3 will also be one of our boundary, and then the plane of x3, x1 will also be one of a boundary, right? And that's because these numbers cannot be negative, right? So that thing is there, but along with that, also the fact that we have this condition, this also gives us a boundary for our reason. Basically, if we can just take the equality equation, and if we plot this, we know that this will just be, okay, so since I can write this as x1 over 1, x2 over 1, x3 over 1, right? So in this form, we know that the plane will intersect at 1, 1, 1. So over here at 1, 1, 1. So, and this will be the plane, right? So yeah, so this is the plane that's given by this equation, right? And since this equation like contains origin, so so the region towards the origin will be our actual boundary. So that means, so just below this plane, so there's this region below this plane, right? Yeah, this three-dimensional region, and this region is also doesn't go like below the x1, x2 plane, or like behind the x1, x3 plane, or just like besides the x2, x3 plane. So this is just the region. The reason is just this thing, and yeah, like this. I mean, I'm making a bit messy, but yeah, you get the idea, I think, right? Now, if I want to write that in terms of integral, so this three-dimensional syntax reason can be written as, first of all, in x1 you can go from 0 to 1, and then okay, and then we know that this thing over here can again be written as, since x3 is 0 at x1 x2 plane, we can write the equation of this line as x2 is equals to 1 minus x1, right? So yeah, for x2 it goes from 0 to 1 minus x1, and now for x3 we can let that go from 0 to 1 minus x1 minus x2, right? Because that's given by this condition over here. And so in this domain, if we just integrate um x1 to the power a1 minus 1, x2 to the power a2 minus 1, x3 to the power a3 minus 1, and then 1 minus x1 minus x2 minus x3 to the power a4 minus 1, and then okay, so did I write, okay, I forgot to write dx1 dx to dx1 over here. I just realized that. So this will be dx2 dx1, okay, and over here it's dt. Okay, fine. Over here now that will be dx3 dx2 dx1, right? And this will be equal to this gamma of a1, gamma of a2, gamma of a3, gamma of a4 by gamma of the sum of all these. Okay, so now we are pretty clear about what we are dealing with, and now let's directly go to the proof. Over here, one thing I wanted you to notice was that this first domain, I mean the first region is always from 0 to 1, right? We can just always like let the first region go from 0 to 1, right? From 0 to 1, right? So please know this thing because this will be helpful in the proof. And now that we already have a lot of experience with this thing, I think the proof should go pretty fast, right? Because we have already spent a lot of time in just knowing what it means, right? Okay. So let's go with the proof. I guess you guys know how the proof by induction works, right? So if you have to, let's say, prove any property P of n, and if let's say there's some base case, in this case greater than equals to 1. So what you do is, first of all, you prove P of 1, and then you assume P of n to be true. That means the formula is true for n being n, and then we prove P of n plus 1 is true. And then we prove that the formula is true for n plus 1. So if we can prove that, so because P of 1 is proved, that means P of 2 will be true, P of 3 will be true, and then it will be true for all natural numbers 1. So, sorry, natural numbers n. This is how proof by induction works. So let's go ahead. So we had to prove that our P of n is, okay, so first of all, let's just state the property that we want to prove. So in n-dimensional simplex, this x1 to the power a1 minus 1, x2 to the power a2 minus 1, up to x1 to the power an minus 1, and then 1 minus x1 minus x2 minus xn to the power an plus 1 minus 1, and then dxn, right? And then dxn minus 1 up to dx1. So this will be equal to, actually what I can also do is, I can also write it in opposite way. It doesn't really matter, right? It's really fine like however I write, because I can just just say that this is actually the domain for x3, and this is for x2, this is for x1, right? It doesn't really matter. I mean, I also have to change these limits. Actually, let me not make it complicated. Let me just go with how it is right now. Yeah. I know. Yeah, okay, okay, let me not complicate. And then dx1. But the thing is, if I write it in a different way, it would have been much easier. But it is what it is. Yeah, let it be the way it is. Okay. And so we know that this will be gamma of a1, gamma of a2. How is it in the main statement over here? Okay, it's in the opposite manner, right? Doesn't really matter. Let me write it in opposite manner. and it's still like these limits, the first one will still be 0 to 1, and this one would have been like 1 minus x2, and this one would have been like 1 minus x2 minus x3, right? So it's the same thing, but yeah, let me write it in opposite manner. Doesn't really matter though. And I'm doing that so that it'll be easier later on while proving. I mean, the notation will be easier. And then up to gamma of a n, gamma of a n plus 1 by gamma of all this sum, right? Okay, so now we need to prove this, right? So how do we begin? So first of all, we have already proved the P of 1 case earlier. We know that this go from 0 to 1 and x1 to the power a1 minus 1, 1 minus x1 to the power a2 minus 1. And we know this from beta function that this is actually just beta of a1 comma a2. And that's just gamma a1 gamma a2 by gamma a1 plus a2. And that's exactly what our formula says. So this is true for one dimension, right? Okay, now for let's assume that this is true for n dimension. So that means in n-dimensional simplex, this formula holds true, right? Xn to the power an minus 1. It's so difficult to write this formula actually because it's so long. So yeah, so this is it's true in n dimension. We assume that, right? Gamma of a n by we have, okay, just a second, just a second. Okay, yeah. So we have this as divided by gamma of a1 plus a2 up to an, right? Okay, so we have this in n dimension, and now we wanna prove this for n plus 1 dimension, right? So in Tn plus 1, x1 to the power a1 minus 1, xn to the power an minus 1, xn plus 1 is also there. So an plus 1 minus 1, and then 1 minus x1 minus x2 up to minus xn minus xn plus 1. That's a lot, guys. And also, I forgot to wrote this dx again. So this will be dx up to dxn, and there will be like dx1 up to dxn plus 1. And this is equals to product of all these gammas up to an plus 1, and then the sum of, okay, I forgot. Okay, again, I'm missing something. Over here, there will also be gamma of an plus 1. Guys, there's a lot of things, so yeah, there's always a chance I will forget something. Right, and that could be messy and like not so enjoyable for the viewer. But what can I don't know. Okay. So yeah, and in this case, there will also be a n plus 2, right? So yeah, there will also be gamma of a n plus a sub n plus 2 by gamma of all this sum, right? Okay, so how do you prove this one? Yeah, so first of all, we know that this one can also be written as like this x n plus 1th coordinate, this last coordinate going from 0 to 1, and rest of them like whatever it needs to be. So that thing, right? So I think it will be like, first of all, it will be from 0 to 1 minus xn, and then 0 to 1 minus xn minus xn minus 1, something like that will be there. But yeah, whatever we need, yes, according to that, so all the limits are there. Okay, so yeah, I'm just trying to show you that the first one will be 0 to 1. So this xn plus 1, x sub n plus 1 is going from 0 to 1. So we know that, right? And I can still write this integral. It's so long, so I'm not actually writing it, but I was just telling that. So now I can actually just copy it, and then I want to show you something that we can do to simplify this integral. Copy, paste. There's a lot of things going on here. Okay, so now we are gonna make a substitution, right? We're gonna make this substitution of xi being 1 minus xk plus 1 times yi. So after we make the substitution, like it turns out yi will, okay, and I will make the substitution for I from 1 to n only, not for n plus 1, right? Or like only for like x1, x2 up to xn, right? And once solving with substitution, turns out like all this set of points yi will still be making nth dimensional simplex, right? So let's see that. And also like this thing over here will simplify. We will see that how. We will see that how. Okay, so let's do it. And in this case, it's not k, actually, it's n plus 1. Okay, and how it will simplify is, if you want to see that, so all of these will basically carry a 1 minus xn plus 1 with it, right? And there's also 1 minus xn plus 1. So what will happen is you'll basically have 1 minus xn plus 1 all over this, and then minus again 1 minus xn plus 1 over all of them times like y1 plus y2, all of it, right? And now if you try to take this common, you will basically just have y1 up to minus yn. So this will basically help us to use our inductive hypothesis. I will see that. Let me not go too fast right now. But yeah, like this will be helpful. So that's why we are choosing to make substitution. And also like, yeah, there are two benefits. First of all, it will like basically make this term simpler, and also why I will still be following the rule for being an dimensional simplex. So let's prove each of that. So yeah, so for like all these yi from 1 to n, we are making this substitution, right? So to make the substitution, we also need to find like the Jacobian and all of that, and how all this limits like change, right? So the last one for xn plus 1, it will still be from 0 to 1, but all others are gonna change, right? So let's see how they are gonna change. So to find that, first of all, we know that for yi, if it's xi by 1 minus xn plus 1, right? And since this xn plus 1 is like uh is like less than 1, right? Because all the sum of all the coordinates was less than 1, so definitely it's less than 1, right? So, and also xi is positive, right? So that means from here we can infer that yi, like every yi is also like positive, yeah? Is also like positive. And also not just this, if you try to take the sum of all these yi up to yn, basically denominator is same for everything, right? So this will just be x1 plus x2 up to xn by 1 minus xn plus n, right? And we know that like since this was the n plus 1 dimensional simplex, this thing over here in numerator, we know that like this, if we had added this with xn plus 1, this should have been less than equals to 1, right? So since we know that from the definition of the n plus 1 dimensional simplex, so this will be less than equals to 1 minus xn plus 1, right? The numerator. Denominator also has the same thing. So we see that this is actually now equal to 1. So this sum y and 1 up to yn, this is actually less than equals to 1, and also each yi is greater than equals to 0, right? So the fact that this criteria is satisfied will like will in from there we can infer that this all this set of coordinates y 1 up to yn actually form a n-dimensional simplex. Form a n-dimensional simplex. And yeah, now since this form n-dimensional simplex, now it will be easier for us, because now all this integral will now be in like n-dimensional simplex, right? From y1 to yn. So now also let's try to find the Jacobian first before we transform the integrals. So to find Jacobian, we know that to find Jacobian, what we do is, so in this case, we want to see how this dx1, dx2 up to dxn will be equals to dy1, dy2 up to dyn, right? So over here, this will just be, there's a symbol, right? uh, of all these y(n). This is a symbol of the Jacobian, x1 up to xn, right? And what this symbol basically means is we will have first of all dy1 by dx1, dy2 by dx2, up to dy partial dy1 by dxn. Again, this will be for y2. Actually, no, I'm sorry. What I'm writing. First of all, it's for all, for y1, there will be all x's, right? And then for y2, there will be all x's again, all x's again. Yeah. Again, for y3, there will be all x's again from 1 to n, right? And yeah, similarly, this goes on up to yn. For yn also we will have all the x's, right? And yeah, and then there's this dy1, dy2 up to dyn, and over here, this will be dx1, dx2 up to dxn, right? Now let's just try to find this Jacobian. So we know that in our substitution it was like for every yi, that was equal to xi by 1 minus xn plus 1, right? So here, from here, notice that if I'm taking dyi with respect to dxi, then it will just be 1 by 1 minus xn plus 1, right? Actually, it turns out I'm writing the order in a different way. Actually, if okay, guys, there's slight mistake again. So basically, I'm writing it in wrong manner. I'll justify you why this is wrong. Just a second. There will be dx1, dx2, all these things over here. I actually mess up a lot. Yeah, okay, and like, sorry. Okay, now how do you know I messed up is how you can see this is you can see it like this, all these d of x1s being cancelled to all these dx1s, and you will have this dy1 left, and which will give this to you, right? So that's how you see it, and that's why I'll notice that this I was actually doing wrong over here, right? And yeah, so let me just correct that everywhere. It might feel like I'm doing a lot of mistakes, guys. Yeah. Okay. So finally we are cool. So now if I'm differentiating dyi with respect to dxi, then that will just be 1 by 1 minus xn plus 1, just because this is just a constant. So, and the derivative of like just x is just 1, right? But if I was doing with respect to any other xi, any other, let's say xj, such that j is not equals to I, in that case, this, like for x3, x2 will just be a constant, right? So this will just be a 0. So I think you get that, yeah? Because like, let's say if I was trying to find partial y3 by partial x2, then partial y3 is just x3 by 1 minus xn plus 1, right? But if j is y2, then definitely that's gonna go to 0, right? And also this, like, this our I is only goes from 1 to n, right? So this xn plus 1 is always a constant no matter what this uh x sub I is, yeah? So I guess you see what I'm trying to say. So that means over here, this one will be 1 by 1 minus xn plus 1, but all these others will just be 0. Over here, this will be 0, 1 by 1 minus xn plus 1, and that will just be 0. So, and again 0, 0, and this is 1 by 1 minus xn plus 1, right? And then dx1, dx2 up to dxn, and then dy1, dy2 up to dyn, right? Now, since this is a diagonal matrix, finding determinant is easier. You should just multiply diagonals, and this will be 1 by 1 minus xn plus 1 to the power n, right? And then that's the dx1, dx2 up to dxn. So now I can write like this dx1 dx2 up to dxn as 1 minus x sub n plus 1 to the power n times dy1 dy2 up to dyn, right? Okay, so we finally have this thing, and that's a big deal for us, right? Okay, so now let's just now we know how the domain changes, we know how the differential changes, and now we can substitute the variables over there, right? And for substituting variable, we know the formula is that the substitution is yi is equals to xi by 1 minus xn plus 1, right? Okay, so now our domain, we know I already told you that xn plus 1 will still go from 0 to 1 for this d sub xn plus 1, right? And for all this dy1 up to dyn, this will now be like our domain of nth simplex, right? For all the others, now our x1 will be okay. Now for all this product of x1 x2 up to xn, so that will just be like xi will just be 1 minus xn plus 1 yi, right? So there will basically be n such 1 minus x of n plus 1, yeah? Actually n or n plus 1, because actually there are n plus 1 such variables. So actually there will be this 1 minus x n sub 1, like there will be n plus 1 such variables, and then y1. And not just that, all these xi's also have some like powers, right? A1, yeah. So I also need to add those powers. And yeah, so okay. Actually, first of all, let me write this thing again, otherwise it's gonna get confusing moving up and down and up and down. Let me just copy this and we'll deal with it, okay? Let's go see. Let's not panic, guys. Yes, I feel like I'm panicking a lot now. Yeah, let's not panic, guys. Let's not panic. Pissed. Pissed. Okay, let me just copy this down because this thing is actually helpful, right? This one is actually necessary. Yeah, and okay. So now we know the substitution, right? What our substitution is. So over here, notice that okay. So this was for I from 1 to n, right? So just for those xi's, we are gonna substitute, right? So we are gonna substitute for these xi's. So there are n of n such, right? So if we substitute that for each of them, like as xi being 1 minus xn plus 1, so we will have 1 minus xn plus 1, and the powers of all these will be added. So a1 from an, and then all these negative 1 n times. So that will be a1 from an minus n, right? And then we will have all this y1 to the power a1 minus 1, y2 to the power a2 minus 1, up to yn to the power an minus 1. But this thing xn plus 1 to the power an plus 1 minus 1 will be as it is, right? Because that's not changed. And then over here also, I can actually first of all write 1 minus xn plus 1, this last variable. And then for all these x1s, we know that for all the xi's, that will be 1 minus xn plus 1 times yi. So I can actually take common 1 minus xn plus 1, and then all of these will be added, y1 plus y2 up to yn. So now, just like I told earlier, now I also need to include the this Jacobian, which is what was the Jacobian, guys? Yeah, 1. Also I need to include that. I shouldn't forget it, right? Shouldn't forget. This is all in product, okay, in the same integral. 1 minus xn plus 1 to the power n. Okay, so now like what I was telling earlier, how this is helpful is now I can actually take 1 minus xn plus 1 common over here, right? And that will simplify, and that will help us to use the inductive hypothesis. So this is from 0 to 1. This is nth simplex, right? If I add this term with the first term, I will have 1 minus xn plus 1, and then a1 up to an, right? And then this is y1 to the power a1 minus 1, y2 to the power a2 minus 1, yn to the power an minus 1, xn plus 1 to the power an plus 1 minus 1. Over here, I can take 1 minus xn plus 1 common. Also, guys, I just realized this had some power as well. Why do I mess up a lot, guys? This also had a power an plus 2 minus 1. Okay. So yeah, this if I take common in this, take out, this will have also power an plus 2 minus 1. And there's this 1 minus y1 minus y2 up to yn, an plus 2 minus 1, right? Okay, they're finally good. And then there's this dy1, dy2 up to dyn, and then there's this dxn plus 1. So I can actually take this xn plus 1 out, right? So we'll have 1 minus xn plus 1 to the power a1 up to an, and there's also this an plus 2 minus 1, and there also xn plus 1 to the power an plus 1 minus 1, right? And inside we have this t1 where we have y1 to the power y to the power a2 minus 1 up to yn to the power an minus 1. And finally we can use the inductive hypothesis, right? An plus 2 minus 1. Am I correct? Yeah, I think I'm correct. Yeah, notice that there's this one term missing. I mean, n plus 1 is missing, but yeah, that's fine. I cannot do anything with that, right? Okay, so dy1, dy2 up to dyn, and then b sub xn plus 1, right? Yeah. We can actually deal with these x's and y's separately because they seem to be completely independent, right? So we can just like do this integral separately, doesn't really matter. Like if there's no like common variable, I mean, yeah, because there's no y used in over here. Okay, so this one will just be beta function, right? So of this thing and this thing. So that will be gamma of a1 up to an plus 2, right? And then this will be gamma of an plus 1 by gamma of a1 an, and also there's an plus 2, but we are also adding an plus 1, right? So this is the first integral. And the second integral, we know from inductive hypothesis that this is equals to gamma a1 gamma a2 up to gamma an, and then gamma an plus 2 by their sum, right? So gamma a1 gamma a2 up to an plus 2, right? Finally, the moment of happiness, because this thing cancels out, because these two cancel out, right? And what we have remaining is what we wanted to have in the n plus 1th term. So gamma a1, gamma a2 up to gamma an, and then this is gamma an plus 1, and this is gamma an plus 2 divided by their sum. Gamma of a1 plus a2 up to an plus 1, an plus 2. And that's exactly what we had to prove in the pn plus 1, right? Yeah, so this is what we wanted to prove, right? And we proved that. So which proves the successive step, right, in the induction. So from here we can say that hence by principle of mathematical induction, we can say that P of n, that means that integral that we want, this Dirichlet integral or generalized beta integral, is true. The formula is true for all n greater than equals to 1. Also, n should be natural numbers because 1 leads to 2, 2 leads to 3, 3 leads to 3 is 4, right? So it's only proof for natural numbers, right? But definitely it's mathematicians' job to generalize and for any real numbers, and yeah, they will just do it, yeah. So we have finally proved this. It was a bit long, a bit messy, and a bit involved, right? But we finally proved this. This is really beautiful formula, guys. So elegant, so beautiful, just looking like a wow. So that was it. Hope you enjoyed the video. Thanks for watching, and I look forward to seeing you in the upcoming videos too.